The topic of the lecture today is problem solving. In physics, we use formulas to describe the relationship between various quantities that are associated with a phenomenon. And so when we want to find one unknown quantity, when we know the rest of the information, we would use an equation or a formula to do so. And not always the formula that we are given is the formula that is going to be useful to find the unknown quantity. What we'll have to do is we'll have to rearrange the terms in the formula in order to solve for the unknown quantity. So then after that, we may have to substitute various values for these quantities in order to find the answer to the question. And so this lecture will basically explain how to approach those situations, how to rearrange terms in a formula, and how basic algebraic operations are used to solve problems. So I'm going to go over different examples of simple algebraic structures and how to deal with those in order to solve for the unknown quantity. Let's start the lecture with the concept of a formula. So in physics and in science in general, we have various phenomena, and so each phenomenon can be described by measurable physical quantities that are related to the evolution of this phenomenon, to how this phenomenon happens and what the results of this phenomenon are. Some examples of measurable physical quantities are temperature, energy, force, speed, torque, pressure, and so on and so forth. And so these physical quantities do not have fixed values. Their values can change in a wide range of values. And so because of that, these quantities are also known as variables. The relationship between physical quantities, also known as variables, are expressed with formulas. Each quantity or variable has an assigned symbol or letter which is used to identify that quantity. And typically in physics, each quantity has a unique letter assigned. There are several examples where different quantities may have the same letter, but they are very few and far between. In this course, we will encounter quantities which have unique letters, so we are not going to have to remember the same letter for different quantities. Now we are ready to define what a formula is. A formula is an equation or expression which is expressed in letters and numbers. And the formula defines the relationship between physical quantities. To solve a problem, we need to use a formula that connects the various physical quantities that are involved in this problem, and we have to solve this formula. So what does it mean to solve the formula? Well, to solve the formula for a given letter means to express the given letter or variable in terms of all the remaining letters. That is, by using the equation solving principles, rewrite the formula so that the given letter appears on one side of the equation by itself and all other letters appear on the other side. So this transformation or rearrangement of the letters in the formula require understanding of simple algebra operations such as cross multiplication, finding a common denominator, and so on and so forth. And we are going to discuss these simple operations with several examples in the next few slides. Let's look at the following example for a formula. This would be the formula that relates the distance an object travels with the speed with which the object travels and the time of travel. So we know that the distance is equal to speed times time. For example, if a car travels at 30 miles per hour for 2 hours, it's going to cover a distance of 60 miles. Now, this relationship is expressed with the words that describe these quantities. However, as I talked about previously, each quantity is assigned its own letter or symbol that is used to identify that quantity. So let's list the symbols that we will use for labeling distance, speed, and time. So the label for distance is d, the label for speed is v, and the label for time is t. And so then I can rewrite this formula with symbols like so. Distance is equal to speed times time. And so this is now a formula. Let's give an example of several different formulas where we also have a combination of symbols and numbers, just to give you an idea of what they look like. Here we have an example of the formula that calculates the kinetic energy of a moving object, where we have the product of the mass of the object, the speed of the object to the second power divided by 2. So this is a combination of symbols and numbers. And this formula here is an example for conversion from Fahrenheit temperature into temperature in Celsius degrees. So we take the temperature in Fahrenheit degrees, subtract 32 from that, and then multiply by 5 and divide by 9, and that gives us the temperature in Celsius degrees. So this is another example of a formula that has both symbols and numbers. So as I talked about in one of the previous slides, solving a formula means to express the unknown quantity, the letter, in terms of the known quantities, their letters. So that may require rearranging the letters in the formula. Let's use for an example the relationship between distance, speed, and time, and see how that works. So we know that the relationship between distance, speed, and time is given with this formula. Distance is equal to speed times time. So let's say that I want to find an expression for the time. So my problem has information about the distance traveled and the speed of travel. And the question is, how long did it take for this moving object to travel that distance? So in order to answer this question, I must find what the time is equal to. And in order to do that, I will have to rearrange the terms in this formula to solve for the time. So using simple algebra operations, I end up with this expression for which I've solved for the time t. And so the time t of travel is equal to the distance d traveled by this moving object divided by the speed with which the object is moving. So for example, if the distance traveled was 60 miles and the speed of travel was 30 miles per hour, then the time to cover that distance would be 2 hours. Of course, I can also ask a different question, and that would be, if I knew the distance of travel and the time for travel, what was the speed of travel? So that will require rearranging the terms differently. Now I want to solve for the speed v. So the rearranging of the terms leads to this relationship. The speed of travel v is equal to the distance traveled divided by the time of travel. So for example, if the distance traveled was 100 miles and the time of travel was 2 hours, then the speed of travel would be 50 miles per hour. So that's what they mean by saying that solving for a variable or symbol may require to rearrange the terms in the formula. So we isolate the variable or symbol that we want to solve for, and then using simple algebraic operations, we arrange the other terms according to the rules of algebra one more time to get an expression which we can use to solve the problem. Now I will talk about some basic algebra rules and operations that we will use through this semester to solve various physics problems and help us with manipulations of formulas. So first I will talk about common denominator. And I will go through these rules by giving you simple examples, just to illustrate the principles of those operations. And you can extend those examples into any problem that you will be dealing with, since the rules apply equally. So the first example reads that 1/4 minus 1/3 is equal to A. And the question is, what is A equal to? Here we have two fractions, simple fractions. And in order to solve for A, we must add those two fractions. So when we are dealing with fractions, the way to add them or subtract them is to find the common denominator for those two fractions. So the common denominator is simply found by multiplying the two denominators. So in this case, one of the denominators is 4, the other one is 3. So the common denominator here would be 4 times 3, or that is 12. So in order to make the denominator of each of those fractions 12, I must multiply the first fraction, the denominator, by 3, and the second fraction, the denominator, by 4. However, if I just do that, that's going to completely change the two fractions, and then I am no longer dealing with the original problem here. So in order to not change the problem, I also must multiply the numerators by the same amount that I'm multiplying the two denominators. So if I'm going to multiply the denominator of the first fraction by 3, I also must multiply the numerator by 3. And so the first fraction is unchanged. And then similarly, if I multiply the denominator of the second fraction by 4, I must multiply the numerator by 4 so that the fraction doesn't change. And so this is equal to A. Okay, so then A is equal to 3 divided by 12 minus 4 divided by 12. Now, since both fractions have the same denominator, I can combine them. And so the two numerators will subtract from each other. So we get 3 minus 4 divided by 12, and that is minus 1 divided by 12. So finally, A is equal to minus 1/12. I plan to show some more examples with finding common denominator where the unknown quantity is not nicely presented as the previous example, but it is in a denominator, for example. But before we can do those, I want to go over some other simple algebraic operations, such as cross multiplication and how to move terms in a formula where things are multiplied or divided around. So the first example I want to show is this following example. A is equal to 3 times B. And so the question is, what is B equal to? All right. So here we have that B is multiplied by 3. So in order to isolate B alone, I must divide by 3 on both sides of the equal sign. And so when I do that, I get A divided by 3 is equal to 3 times B divided by 3. And so on the right-hand side, I have 3 in the numerator and denominator, so those will cancel out. And then what I'm left with is that B is equal to A divided by 3. And so this is my answer. So here you can see that since B was multiplied by 3, in order to quote-unquote get rid of the 3 here on the right-hand side, I had to divide by 3. And I also have to divide by 3 on both sides of the equal sign, because otherwise the relationship is going to completely change. So here is a different example. This time A is equal to B divided by 4. And again, I want to solve for B. So now notice that B is divided by 4. So therefore, if I want to isolate B alone on the right-hand side, I must multiply both sides by 4. And what I will get is 4 times A is equal to B divided by 4 times 4. So here we have 4 in the numerator and the denominator, so I can cancel these out. And the final result is that B is equal to 4 times A. I want to make a note regarding how I did the algebra right here. So whether I'm going to write B over 4 times 4 this way, or B times 4 divided by 4 that way, those are identical. So when you have something like the left-hand side here, you can always write it as the right-hand side here, and then do the operations if that is easier for you to see. Now let's look at an example that is basically the same example as the previous one, except for here we don't have any numbers, it's all symbolic. So the relationship is that C is equal to D divided by F, and I want to solve for F. The only difference from the previous example is that the unknown quantity is in the denominator here. So in order to isolate F, I must multiply by F on both sides. So this will be a several step problem, not as limited number of steps as the previous example. So I must multiply by F on both sides. So C times F is equal to D divided by F times F. So I have on the right hand side F in the numerator and denominator, so those two cancel out. Remember, that's the same quantity with the same value, so they cancel out. And so now I have C times F is equal to D. So now we see that C multiplies F. So in order to isolate F alone on the left-hand side here, I must divide both sides by C. So let's do that on the next row. So C times F divided by C is equal to D divided by C. Again, C is in the numerator here and denominator here, so cancel them out. And so finally, we have the result. So F is equal to D divided by C. If you are familiar or more familiar with cross multiplication, you will notice that all I really did through all those steps here was switch the places of F and C. They basically moved as if that is a cross or one arm of a cross. So they just switched positions. So all of these operations resulted in that result. So that is the net effect. So any type of problem where we have a relationship that is only based on multiplication or division, multiplication in division is done by using those steps. If a number or a quantity that we want to move is in the numerator, we must divide both sides by that quantity. And if a quantity or a number is in the denominator, we want to move that, we must multiply by that quantity on both sides. It is very important to remember that the multiplication or division must be done on both sides at the same time, because if it's not, if you only do that to one of the sides of the formula, then the entire relationship changes and it's completely different relationship. All right, so now let's look at a different type of relationship, one in which we have addition. So A is equal to B plus 3, and I want to find what B is equal to. So I must isolate B on the right-hand side here, leave it alone, and move the 3 on the left-hand side where A is. Well, since I'm adding 3 to the left-hand side, if I subtract 3 on both sides of this relationship, that will leave B alone on the right-hand side, and it's going to give me the expression for b. So a minus 3 is equal to b plus 3 minus 3. Plus 3 and minus 3 give us 0. And so finally, we have that b is equal to a minus 3. That's the final result. Now here I want to make a very important point. When we are subtracting like so, we are doing the subtraction after all the terms that are present on that side of the formula. So a here on the left side of the formula, I subtract 3 from a and I write the 3 behind the a. So I've seen students do something like this. They say 3 minus a when they mean a minus 3. This is completely different relationship. It changes the entire relationship between a and b if it's done this way. So you have to be always very careful when you do subtractions like so, and always put the subtracted quantity behind everything else that is on that side of the equation. So this here is incorrect way of setting up the problem. Another example is the following relationship. C is equal to d minus 5. And the question is, what is d equal to? So this is the same problem as the previous example, except for now we have a subtraction here. 5 is subtracted from d, and it's not added. All right, so then in order to isolate d alone here on the right-hand side, I need to add 5 to both sides of this equation. So c plus 5 is equal to d minus 5 plus 5. So again, minus 5 and plus 5 will cancel out, and the result of this calculation is that d is equal to c plus 5. Now here, since I'm adding to both sides, there is no danger of messing up signs. So 5 can be placed in front of c on the left side or behind. I personally recommend, for consistency, to keep it the way I explained on the previous slide and do the addition behind all the terms that are already on the left side, or whichever side it is. So now let's look at the following example. 3c plus 2 is equal to 5b, and I want to solve for b. So here we now notice that b is multiplied by 5, and so by the previous example that I showed you, in order to have b alone here on the right side, I must divide both sides by 5. So let's see what that looks like. So you have 3c plus 2. I'm going to look at this as one whole expression. So I'm going to place it in parentheses. And then I'm going to divide this entire thing by 5. And then on the other side, I have 5b divided by 5. So I have 5 in the numerator and denominator. They cancel out. And so the final result here is that b is equal to 3c plus 2 divided by 5. Here, it's very important to notice that I divided the entire left-hand side by 5. It is very common for students to divide only one of the terms by 5 and leave the other one alone, but that changes the relationship entirely. So remember that you must divide the entire left-hand side or right-hand side, whichever side it happens to be, by the number you're dividing by, not only parts of it. So the next example is a little bit more complicated as far as algebra is concerned, because it requires a few extra steps compared to previous examples in order to find the unknown. So here we know that 5a plus 3 is equal to b. And so the question is, what is a equal to? So now notice we have two different types of operations. We have a multiplied by 5, and then 3 is added to that result. So, in order to solve for a, I must move the 3 and the 5 on the right-hand side. So, the order of operations here is important. First, I must deal with terms that are either added or subtracted. In this case, 3 was added to 5 times a. So first, I must move the 3 on the right-hand side. Since the 3 was added here, that means that if I subtract 3 from either side, that's going to cancel the 3 out from the left-hand side. So let's write it down. So we have 5a plus 3 minus 3 is equal to b minus 3. So again, notice that I keep the subtraction here. I subtract 3 from b and I keep it behind the b. I don't place it in front. All right, so on the left-hand side, we have plus 3 and minus 3, so those cancel out. And so then that results in the following relationship. 5a is equal to b minus 3. So now recall the previous example from the previous slide where I have the unknown quantity multiplied by a number. So in order to have only the unknown quantity alone on the left-hand side, I must divide both sides by 5 here. So what I get is 5a divided by 5 is equal to b minus 3, that whole thing divided by 5. So on the left-hand side, we have 5 in the numerator and the denominator, so those will cancel out. And finally, my expression for a, my formula for a, is that a is equal to b minus 3 divided by 5. Here is a different example, which is also to reinforce the importance of order of operations. Here we have that z is equal to 2/5 of b plus 11. And what I want is to solve for b. Okay, so in the previous example, on the previous page, let's go back to it, I had 5a plus 3 was equal to b. The first step was to take care of the 3 here on the left-hand side and then deal with the 5. But now the situation is very different. Here I have b plus 11 in parentheses, which means that I can't straight up work with the 11 here. What I first must deal with is the 2/5 that multiply b plus 11. So I'm going to use the rules that I already explained in a few examples. Since 2 is multiplying, in order to move it on the left-hand side where the z is, I must divide by 2. So let's do that step by step. So z divided by 2 is equal to 2/5 b plus 11 times 1/2. So this is equivalent here to dividing by 2. So we have 2 in the numerator, 2 in the denominator. These cancel out. So let's rewrite and see what we have now. We have z divided by 2 is equal to b plus 11 divided by 5. And here I have what's left is multiplied by 1. I don't write that here because it's understood. And we know that any quantity multiplied by 1 remains unchanged. Okay, so now I have 5 in the denominator here. I must move it on the left-hand side. So since 5 is dividing, in order to move it, I must multiply by 5 on both sides. So we have z divided by 2 times 5 is equal to b plus 11 divided by 5 times 5. So here we have 5 in the numerator and denominator. These cancel out. And so what we have now is 5 halves z is equal to b plus 11. So here I slightly rearranged the terms in order to look, nicer. All right, so b plus 11, we have to deal with that now on the right-hand side. So since 11 is added to b, in order to move it on the other side, I have to subtract 11 on both sides of this relationship. And so when I do that, what I get is that 5 halves z minus 11 is equal to b plus 11 minus 11. And so plus 11 and minus 11 cancel out. And now I arrive at the final relationship that solves for b. And that is 5/2 z minus 11 is equal to b. So here, that's an example of the importance of doing the order of operations correctly. So one more time, since b plus 11 is in parentheses, first I must deal with the 2/5 in front of the parentheses and then move inside the parentheses and deal with what's left. Now here is a different type of problem. So my relationship is that a is equal to 3 times b to the second power, and I want to solve for b. So notice here now that we're dealing with power notation. So my first step, of course, will be to move the 3 from the right-hand side to the left-hand side. And so since 3 is multiplying on the right-hand side, in order to move it, I must divide by 3. So a divided by 3 is equal to 3 times b squared divided by 3. We have 3 in the numerator and denominator, those will cancel out. And so what I'm left with is that a divided by 3 is equal to b to the second power. The question is, how do we deal with that second power here? Well, it turns out that there is an operation that would remove the second power, and that operation is called square root. So square root. And so on your calculators, there is a button that has this symbol, and that is the symbol for square root. Okay, so then if I square root both sides of this relationship, on the right-hand side, I will have b as the result of the square root. And then on the left-hand side, I will have square root of a divided by 3. Let's see what that looks like. So square root of a divided by 3 is equal to square root of b squared. Again, as I said, the square root operation is opposite to taking the second power of some quantity. So then that means that I have square root of a divided by 3 is equal to b. So that's how you deal with those situations. So now that we are familiar with the principles of cross multiplication and how to move parts of an expression from one side of the equal sign to the other, let's look at several more examples of common denominator calculations that require use of more of these operations that I already explained. So we have that 1/7 plus 1 over a is equal to 1/9, and I want to solve for a. So the first step would be to move the 1/7 from the left-hand side to the right-hand side. So since it is added to the left-hand side, if I subtract it on both sides, that will effectively move it to the right-hand side. So we have 1/7 plus 1 over a minus 1/7 is equal to 1/9 minus 1/7. So on the left-hand side, we have 1/7 minus 1/7. Those cancel out. And so what we are left with is that 1 divided by a is equal to 1 divided by 9 minus 1 divided by 7. So now on the right-hand side, I have subtraction of two simple fractions. So before I can calculate a, I must perform a common denominator calculation here on the right-hand side. So again, the common denominator was simply the product of the two denominators. And so in this example, the common denominator would be 9 times 7, which is 63. So in the first fraction, in order to make the denominator 63, I must multiply by 7. But then that also means that I must multiply the numerator by 7, otherwise the fraction is going to change. And then in the second fraction, in order to get the denominator to be 63, I must multiply by 9, which means that I also must multiply the numerator by 9 in order to not change the fraction. And so then this becomes 7 divided by 63 minus 9 divided by 63. And so when I add the two fractions together, I end up with 1 over a is equal to negative or minus 2 divided by 63. All right, so now I want to solve for a. So that means that since a is dividing here, I must multiply by a on both sides. So let's do that. So a divided by a is equal to minus 2 divided by 63 times a. So from here I get that 1 is equal to minus 2 divided by 63 times a. So now in order to have a alone on the right hand side, I must take care of the minus 2 divided by 63. I'm going to do that in one step. Basically what I will do is I will multiply by minus 63 divided by 2 on both sides. So let's see what that looks like. So on the left hand side I have 1 times minus 63 divided by 2. On the right hand side I have minus 2 divided by 63 times minus 63 divided by 2 times a. So on the right hand side I have 2 in the numerator here and denominator here, those cancel out. I also have 63 in the numerator here and denominator here, those cancel out. And those two minuses multiplied together will give me a plus. And so now finally I have an expression for a, and that is that a is equal to negative 63 divided by 2. That's the final result. So if you follow the rules of the algebraic operation ordered properly, and you do all your calculations properly, this problem is actually very simple. I just did it in multiple steps, very detailed, so that you can see how to approach it. Of course, if you have a different way of doing it that leads to the correct result, you're free to use it. There is more than one way to do a problem. When we are solving physics problems, or any other problem as a matter of fact, it is important to be able to understand what information is provided in the problem via diagnostics. If it's a written problem, you read it, you write down the information that you know, and then identify which formula to use. And then it's important to be able to rearrange the terms in the formula if you have to solve for certain quantity. And then it's important to know how to substitute the known information into that formula in order to solve your problem. So an important part of problem solving is substituting the given data into the appropriate formula to find the value of the unknown quantity. There are two ways of substituting data into formulas to solve for the unknown quantity. So first would be to solve the formula for the unknown quantity, which is basically what I did so far in all the examples that I showed, and then make the substitution of the data. And then there is essentially the opposite way of working. That would be to substitute the data into the formula first and then solve for the unknown quantity. So in this course, in the textbook examples, and also the examples that I will show you throughout the various chapters, the way they do the examples is by solving the formula for the unknown quantity and then substituting the known data to find the answer to the problem. Now, the first method of substituting data in a formula is more convenient when using a calculator, because entering all the numbers into the formula and then solving for the unknown is practically impossible with a calculator. But if you're doing it by hand, working with all these numbers there and the units that are added on top of that can make it confusing as to what exactly are you doing. And so my personal advice is that it works much better if you learn to identify the formula that you need for the solution of the problem, then solve for the unknown quantity by moving the different quantities in the formula around. And then after you have that down, substitute the data provided in the problem statement and then find the unknown quantity. So here an example of a problem which I will do by substituting known data into the relationship to find the unknown quantity. So I know that A is equal to the product of B and H. And I also know that A is equal to 120 square meters. And B is equal to 15 meters. And then the question is to find H. So first of all, I just look at the units and I see that A has units of area, meters to the second power, square meters. So these are units of area. I also look at B and I notice that it has units of length. So I remember that area was calculated by multiplying two lengths. For a rectangle, that would be the long side by the wide side, which then means that when I solve the problem, when I find H, that would have to have units of meters as well, so units of length. All right, so since I'm solving for H, and my relationship here does not give me H directly, I must rearrange the terms in order to have H alone on the right-hand side, and B has to move to the left-hand side where A is. All right, so A is equal to B times H. And so since B and H are multiplied by each other, in order for B to move to the right-hand side, I must divide both sides by B. So divide by B, divide by B. I have B on the right-hand side, I have B in the numerator and denominator, so those will cancel out. And so now I have an expression for H. And that is H is equal to A divided by B. All right, so now I'm ready to substitute the values of A and B into that formula. So then this becomes 120 meters to the second power divided by 15 meters. So here notice that in the numerator I have meters to the second power, which is essentially meters times meters. In the denominator I have only meters, so that means that the second power in the numerator and the meters in the denominator will cancel out. And what I'm left with is meters for the units of H. And so if I divide 120 by 15, that would be equal to 8. So the result is 8 meters. So H is equal to 8 meters. And so these are units of length as expected. And so that's how we would approach problems through this course. We have a formula that relates certain quantities. We may have to rearrange the terms in order to solve for the unknown quantity symbolically. And then we are going to substitute the known values into that formula to calculate the final result. When we solve problems this semester, we are going to use a simple step method which will allow us to clearly analyze a problem, identify the known quantities, the unknown quantity, select a formula that we will use to solve the problem, and substitute the known values into that formula to find the solution to the problem. So I want to talk about this method and discuss briefly the steps involved. The first step is always to read the problem. And it's very important to read the problem very carefully. While this might be extremely obvious that one must read the problem, very often students do not read carefully enough to understand what the problem is asking, and students sometimes make assumptions of what the problem is asking due to the fact that they did not read carefully. So it is important to develop a habit to read the problem more than once, actually at least 2 times. So the first time you read the problem straight through from beginning to end, and do not stop to think about setting up an equation or formula. So you're only trying to get a general overview of the problem during this first reading. And then read through a second time, but this time slowly and completely, beginning to think ahead of the following steps. So where appropriate, make a sketch. So some problems may not land themselves to a sketch, however, make a sketch whenever possible. Many times, seeing a sketch will show you if you have forgotten important parts of the problem and may suggest the solution. And this is very important part of the problem-solving process, and this is often overlooked by students, and that leads to problems later through the solution because certain details are forgotten. The next step is to write all given information, including units. This is necessary to have all essential facts in mind before looking for the solution. There are some common phrases that have understood physical meanings. For example, the term from rest means the initial velocity is equal to 0. Initial velocity is equal to 0. The term smooth surface means there is no friction. You can assume that. The term it moved until it stopped or to rest means that the final velocity of motion is 0. The term uniform or constant velocity means that there is no acceleration, and so on and so forth. Step number 4 is to write the unknown quantity asked for in the problem. So many students have difficulty solving problems because they do not know what are they looking for, or they are solving for the wrong quantity. That's why it's important to make a list of what you know and the values of those quantities and what you're looking for. All of these labeled with their symbols, so that when you look at the formula that relates those quantities, you know where each value for each quantity goes, and then how you solve your problem. Step number 5 is to write the basic equation or formula that relates the known and unknown quantities. So in your formula sheet, you will find the basic formula or equation to be used. And how do you find out what that equation is? Well, by looking at your list of known and unknown quantities. And so then look for a formula or equation that relates those quantities. And sometimes, which we will encounter a few times through the semester, you may have to use 2 formulas to solve your problem. One would be to find an unknown quantity that then you will use to find the main unknown quantity in the problem. Once you have the formula that relates all the quantities together, find a working equation by solving the basic equation or formula for the unknown quantity. So for example, we know that distance is equal to speed times time. So that would be the basic equation or formula. But if we wanted to find the time, then that would require to rearrange the terms in the basic formula. So that time is equal to distance divided by speed. And that is called the working equation, which can be used to find the time of travel in this problem. Step number 7 is to substitute the data in the working equation, including the appropriate units. So in order to ensure that your answer has the correct units, when you're substituting data in a formula, you must include all units, because you can then do the operations with units to end up with the unit for the final answer. And if you're solving a problem about motion, and if you're looking for time, you know that the unit for the answer must be a time unit. So if you get a unit of length, that means that your calculation was wrong. You plugged the known data in the wrong places. Or if you have to solve a problem about speed of motion, but your answer has distance units, it means that you plugged your data in the wrong places. That's why it's important to have your data entered in the formula along with their units in order to be able to calculate correctly. Step number 8 would be to perform the indicator operations and work out the solution. So although this will be your final written step, you should always ask yourself if your answer is reasonable. Because here and on the job we will be dealing with practical problems, and so a quick estimate will often reveal an error in your calculations. And finally, step number 9 is to check your answer. The question that you should ask yourself is, did I answer the questions? Did I find what I was asked to find? Or did I find something else? Did I present the answer in the correct units? Or did I present the answer in some other units? So always check your answer. And so this concludes this lecture. You guys will get a lot of practice in using those steps by seeing how I do example problems and by working through problems yourselves. And you will develop a good habit of going through the steps, and you'll see how that makes problem solving pretty straightforward and easy in this course.